I'm Alex Keesling. I'm the Chief Science Officer. If I have a pedal for every single wheel, and suddenly I need to drive an 18-wheeler, I do not know how I would do that. Like I have a hard time imagining how it would work even for a car. Imagine an 18-wheeler. For a quantum computer, you want the same principle. You want very few simple controls that make the whole system operate reliably and robustly. And the way that our quantum computers work leverage the flexibility of being able to, number one, use qubits that do not need to be manufactured. They are individual atoms. We take the fundamental unit of matter of a single atom and we convert it into the fundamental unit of information in a quantum bit. And we don't need to build it. They're just there. They're given to us by nature. Every one of them is identical to every other. We don't need to keep track of, oh, where was this atom 2 hours ago? It's just an atom and it's just as good. So that's one thing. It reduces the type of manufacturing that we need to engage with. But beyond that, we do not have a physical substrate on which a chip is built. We have what I like to call a software-defined architecture, where we decide where every qubit is and we have the ability to actually move them around. And we do this with optical tools, which are very highly parallelizable. Think about an overhead projector. How many pixels can you have with an overhead projector? And that is happening with a single source of light, a single light bulb. Yes, what we build looks a little different because we're not using a light bulb, we're using a laser, but the principle is the same. Splitting light is much easier than routing cables. And we use that in a way that allows us to scale. So I think it's important to make a distinction between a system that is scalable and a system that is extensible. If I want to use a computer and all I have is my laptop, I would like to have a scalable system where if I reach a limit, I can simply exchange some component in my laptop and double the power, for example. That is scalability. If to increase my power, I need to get another laptop and have two, well, that is extensible. I duplicated the complexity and the complication and got double the power, but it's not scalable because you just cannot take that so far. What we build is scalable in that we can add more controls without having to double or triple or increase the number of components in a commensurate way. And this is also true for how we control the qubits themselves for the single qubit operations, for the 2-qubit operations. We have a way of doing things in parallel where we have a single or a very limited number of controls that need to be calibrated, that need to be tracked, and they are reliably performing high-fidelity operations on all of our qubits simultaneously. So these characteristics of combining the simplified manufacturing process, the small number of classical controls that need to be calibrated, and the scalability also in the number of qubits combined in a very, very powerful and flexible platform.